So good morning, afternoon, evening, everyone, depending on where you are. It's actually good morning for me, but I think it's good afternoon for you. And if I am correct, I'm the last talk of the workshop. Okay, so yes, I was saying, so hi. It's nice to give this talk and see so many old friends around, even though we cannot make this in person, right? But at least we can meet via Zoom. So thanks a lot, really, to the organizers for the invitation. It's always, well, it's not an invitation, but for letting me talk here. But it's always a pleasure to talk to you guys. And hopefully next time we can meet each other in person. All right, so today I want to explain you about recent results on tensor network simulations for quantum matter that we have been working at my group at the IPC, okay, during the last year. And well, you will see this involves simulations for higher dimensional systems, essentially using PEPs. And of course, if you have any questions or comments, just let me know. Let's get started. This is the outline of my talk. So first, I want to explain you some basic concepts. I don't think I have to explain this to this audience, since this is a tensor network workshop. But since many times there are new people coming to the field and so on, it's never it doesn't hurt at least to repeat a couple of slides that I think they are a good summary of what is going on in the field, right? Then I will move on to the actual more scientific part. First, I will explain you in point number 2 about the breathing Kagome antiferromagnet simulations that we did for this system using project entangled pair states. Then I will explain you about an algorithm that we developed to simulate, well, to compute thermal states of three-dimensional systems on arbitrary lattices, and how we applied this to bosonic models and also to higher dimensional Kitaev models. And last but not least, I will explain about incorporating SU2 symmetry in two-dimensional PEPs and to implement simulations, okay, for complicated SU2 invariant 2D models. As you will see, there are some controversies there that we are still discussing, and yeah, that's what I will be talking about. Let's start with the basics. So I don't think I have to explain you what tensor networks are. Just to remind you that, well, you know, tensor networks are a very efficient way of actually decomposing the coefficient of a quantum many-modic wave function, where instead of having a very big tensor, we just decompose it into the fundamental pieces. The tensor network superstar, as you know, is the matrix plot state behind so many different approaches to simulate one-dimensional systems or even two-dimensional systems, as we were seeing in the previous talk. There are physical and bond dimensions. The bond dimensions are the ones that are responsible for carrying the entanglement in the network. We can generalize this to higher dimensional systems, to PEPs or tensor product states, and also to scale invariant systems via the MERA, the multi-scale entanglement renormalization ansatz, and much more, as you know. So the nice thing about tensor networks is that they are efficient. One can describe them in a polynomial number of parameters, polynomial in the relevant parameters to describe the system. They satisfy the area law for the ground state for the entanglement entropy of the wave function, okay? And they also correspond to low energy eigenstates of Hamiltonians with local interactions, as you know. Nowadays, tensor networks is a very open field, actually, that is finding applications much beyond condensed matter physics and strongly correlated systems. And this is something that you know already. Every time I give this talk, I always have to add one more arrow here. The one that has appeared very recently, well, is the one that has to do essentially with deep learning, artificial intelligence, linguistics, and so on, and also in finance. We are starting to apply this to do actually very complicated finance calculations, such as optimizations and also some machine learning stuff. But I have to say that I will not talk about that here, but in machine learning, turns out that tensor networks are being very successful. One can improve a lot the performance of standard let's say neural networks, for instance, or other types of structures by using tricks that we've been playing with for many years in condensed matter physics, actually, to simulate strongly correlated systems. So that's actually very nice because, you know, the tensor network community is kind of offering things to places where it was not, in principle, interested. But of course, that's always very good. So let me move on to the actual content of my talk, okay? Let's start with the breathing Kagome antiferromagnet. This is the first problem that I want to tell you about. The breathing Kagome-Heisenberg antiferromagnet is just a generalization of the usual Heisenberg quantum, well, the Heisenberg-Kagome antiferromagnet. Okay, we have a Kagome lattice, and we have the spins 1/2 at the vertices of the Kagome lattice, and we have a Heisenberg model defined on this Kagome lattice. So essentially, we have nearest neighbor spin 1/2 spin-spin interactions. The model is SU2 invariant, and there are, well, the difference with respect to the usual Kagome-Heisenberg antiferromagnet is that, you know, the Kagome lattice, you can understand it as a lattice of corner sharing triangles. You have upper triangles, all right, and also lower triangles. And the point is that in the breathing system, the coupling in these two types of triangles is different. So you have one type of coupling for the upper triangles, is this J up right here, and you have a different coupling for the triangles pointing down, which is this J down right here. Okay, so this is why the people call that the lattice is breathing. All right. Now, why is this interesting? Well, this turns out to be interesting for a number of reasons. First of all, as you can imagine, nature is not completely homogeneous, and compounds, Kagome compounds that we find in nature, they tend to be anisotropic, okay, just by construction. So they tend to have some small breathing anisotropy, all right? There is a candidate material also for this type of system, which is this vanadium oxyfluoride compound that I'm not going to dare to pronounce the formula here, but it has been studied actually already in several places as a candidate for the breathing Kagome antiferromagnet. And now there is, of course, a theoretical question that I think is very interesting, which is, well, you know, the Kagome-Heisenberg antiferromagnet, the ground state for spin 1/2. Nowadays, I think it's pretty clear that it's a quantum spin liquid, having lots of calculations of that, and I will revise that afterwards again. Another point is what happens if you introduce a breathing anisotropy, okay? Can you also have a quantum spin liquid, okay? Or you know, does this quantum spin liquid break down at some point with this anisotropy? Is there a quantum phase transition or a first order phase transition going on? Well, the point is that, yes, in nature, there are experimental signatures of a quantum spin liquid at this value of the anisotropy, okay, J down over J up around 0.55. So this is a pretty strong breathing anisotropy already. This is the breathing Kagome lattice, and it looks like it's a quantum spin liquid, okay? So of course, we would like to understand how large is this quantum spin liquid phase. We know that when the anisotropy is very large, essentially this is a crystal of upper and lower triangles, okay? They just decouple. But you know, at some point there must be a transition to the quantum spin liquid, okay? So how is this transition? When does it happen? How large is the quantum spin liquid phase? How large is the other phase, and so on. All right, so this is a good problem to analyze with PEPs. Now, this is a summary of numerical results that we obtained with Said Jaromi, who I think was also talking in this conference. Didier, Paul Blanc, and also Frederic Mila. We published that in SciPost, actually, already a couple of years ago, but it was more a year and a half. So this is a summary of what happens in the small breathing limit. So the small breathing limit is essentially the isotropic limit, where you have the same coupling for upper and lower triangles. This is exactly the Kagome-Heisenberg antiferromagnet, the famous one, where you have, you know, spins 1/2 everywhere and the same coupling everywhere. And whether we want to know, you know, we know that the ground state is a quantum spin liquid. But just to confirm, these were some simulations being carried using project entangled pair states and also project entangled simplex states, okay? And here you have a summary of the results that the people have been obtaining. Down here, we have some DMRZ results, okay? Here on the right-hand side, you can see a summary of proposals for the ground state. Essentially, the people that have been claiming that this was a quantum spin liquid. Some people claim that this was a gapless U1 quantum spin liquid. Some other people claim that this was a gap Z2 quantum spin liquid, and so on. In our simulations, well, what we observe is that the best ground state energies were obtained using this method, essentially project entangled simplex states, and then contracting the environment with corner transfer matrix renormalization group proposed by people in the audience. We went up to bond dimension 13 here. We were not incorporating any symmetry, and just this was just a cross check that our techniques were working, and we were actually getting very close to the DMRZ bounds. Now, we also saw that the decay was algebraic with the bond dimension, and as people have been claiming around, this may be an indication that the ground state is actually gapless. Okay, even though it's not a proof, but it may be an indication. So we take it that our simulations can essentially reproduce the gapless quantum spin liquid here on the right-hand side of the phase diagram. Now, what happens on the other side? What happens if in the limit of a large breathing limit? Okay, so we did simulations for J down over J up equals 0.01. This is a very large anisotropy. Okay, and this is a summary of the results that we found. Also, compared to results by different people. All right. Some people were proposing here different types of states for the ground state at this particular value of the breathing anisotropy. Some people were proposing a quantum spin liquid, other people were proposing valence bond crystal, a nematic phase, and so on and so forth. Our simulations, the one that is working better for us is the one, again, using project entangled simplex states plus corner transfer matrix renormalization group. The extrapolation, it's actually going very down, even lower than most of the previous calculations that I'm showing here. The extrapolation is very much compatible with the DMRZ result. Okay, that is right here. This was a paper by Cécile Repelin in 2017, where she was proposing that the ground state is a nematic phase. Okay, and that's actually what we find also for this ground state. We do extrapolation, and that's exactly what we find. We find this type of structure in the ground state. It's a lattice nematic state. It's a state that preserves the translational symmetry along one direction. Well, actually along both directions, but you can see that they are pretty different. But because it breaks precisely rotational symmetry. All right. So there are different types of bonds right here, and this is exactly the phase that we predict, and it's very much compatible, if not the same, that was predicted by the DMRZ result. So with project entangled simplex states in 2 dimensions, our prediction is that the ground state of this large breathing limit phase is actually a gapless nematic state. Now, the phase transition happens to us around 0.05. This is very low, all right? And it's actually compatible also with the experiment on the quantum spin liquid. So there was experimental evidence of a quantum spin liquid ground state around 0.55. That's perfectly fine. It's right in the middle of our computed quantum spin liquid phase, okay? And then we detected that there was a transition right here. So we could see this in different ways. For instance, by having a look at the spin-spin correlators, we see a discontinuity going on. But we also had a look at entanglement entropies, and we saw that there was a peak and so on. We didn't study the nature of the transition yet. So we are still not sure whether this is a first order or a second order quantum phase transition and how it behaves. But we know that the phase transition is happening here. And moreover, we also noticed that the quantum spin liquid phase is really super large. So if you compare it to the nematic phase down here, the gapless nematic phase is actually pretty small, whereas the gapless quantum spin liquid phase, it extends for most of the phase diagram. So this quantum spin liquid is really very, very robust. Okay. Moreover, we also studied the correlation functions in the nematic phase, and we found that they are critical. So by studying the correlation function, the spin-spin correlation function along the horizontal direction, which is this direction where we are actually observing these chains, okay? Actually, even though this is a PEPS calculation, and this is hard to reproduce a critical correlation function numerically with a numerically optimized PEPS, we are actually getting indications that, yeah, this looks like it could be critical. Okay, and that's actually what we are seeing here with a given critical exponent, that it looks like something between 2.2 and 3.5. So the nematic phase is critical. There is a phase transition here at 0.05, and eventually it goes to a gapless quantum spin liquid phase that is super large. All right, so these calculations were done with project entangled simplex states, and they were published in SciPost. Let me move on now to the second scientific content, let's say, of my talk, which is about thermal states. This is again something that we published with Said some time ago. We developed an algorithm actually, before doing thermal states, we developed an algorithm to deal with infinite lattices of any in 2 dimensions or even in higher dimensions of any geometry. Okay, and then we generalized this algorithm to dealing with thermal states. So we developed an algorithm to deal with thermal states in arbitrary lattices. This includes higher dimensional lattices, such as the cubic lattice in 3D, or even the pyrochlore lattice, okay, or even more complicated ones. So we developed this algorithm for computing thermal states. It's based on just the standard tricks for computing thermal states using tensor networks, which have been used, for instance, in 1D very intensively using matrix product operators. But now we generalize that to 2 dimensions with project entangled pair operators. It's based on the simple update. All right. So we have to apply gates on a project entangled pair operator representing the state, both on the Ket and the Bra indices. Now we choose to use the simple update because it's very convenient in order to deal with different lattices. And we know that this is approximate, but for the systems that we want to simulate, this was already sufficient. And the way to compute expectation values was by approximating them through a mean field environment, which is essentially what we have here on the lower right corner. We know that this is approximate. We are not contracting the full lattice using corner tensors or similar techniques. But we know that this is going to be okay if the correlation length is sufficiently small or not too large. And posteriori, we're actually testing for which systems this is actually working. As you will see, surprisingly, in higher dimensional systems, even though this is a very crude approximation, and we are forgetting a lot of entanglement here, as you know, there is entanglement monogamy. And when you increase the dimensionality of your system, the bond dimension of your tensor network also tends to go down. The correlation, because the correlations are more diluted, okay, through the different sides of the network. Eventually, you hit mean field theory for sufficiently high dimensionality, and this is the reason why we are doing this. This is what is motivating us. We think that in higher dimensional systems, these approximations are actually better motivated than, let's say, in 2D or even in 1D. Okay, so that's the algorithm that we used. We applied it to simulate a thermal system of 3D bosons. And here you have an example of some of our calculations for the soft core Bose-Hubbard model on the cubic lattice. Okay, so here the Hamiltonian is the standard one for bosons that you already know. There is a hopping term, and then there is a density-density interaction, and then there is a chemical potential term. Now I have to say that we did simulations for hardcore bosons and also for softcore bosons. Here you have an example for softcore bosons actually for the cubic lattice, okay, in 3D. At different temperatures. So the first diagram here is essentially, this is the composition number as a function of chemical potential versus hopping, okay, in units of U. This is at 0 temperature, and you can see that we are doing soft-core bosons with occupation number up to 2, so there can be either 0, 1, or 2 bosons per lattice site. You have here the 2 different mode lobes, okay, as you will expect from this system. Here is the tip, all right, which is very interesting. Now, what we are able to do with our algorithm is to switch on the temperature and to ramp it up. And effectively, this is what we get at 0 temperature. We see very clearly the 2 lobes, okay? But as we switch on the temperature, we see that the 2 lobes start to melt, okay? They melt with each other. And that's exactly what we see already for very low temperatures right here in B, in 0 at temperature in units of U, 0.1. Again, this is melting. At temperature 0.2, this is completely melted, all right? So this is a calculation that we are able to do with our algorithm. We are able to see how the effect of the temperature is actually to melt the 2 lobes in the Bose-Hubbard model in the cubic lattice. We did more calculations. This is an example of calculations in the cubic lattice and also on the pyrochlore lattice in 3D, which is highly frustrated. Again, for the cubic lattice, for the soft core bosons that I was mentioning before, for occupation number up to 2. All right, here you have an example of calculations for the occupation number and also for the superfluid density. Essentially, what you can see is that once you start switching on the temperature, the superfluid density disappears. Okay, the superfluid phase disappears. And also, you start to have these intermediate gas phases right here. where the completion number is, somehow interpolating between 0 and 1 or between 1 and 2. We did the same calculation for the pyrochlore lattice, where we this time we only did hardcore bosons. Actually, we will also do softcore bosons, but I think we just do hardcore bosons for for demonstrative purposes. And again, we see the same type of effect. So the superfluid phase at 0 temperature is very well established with our algorithm. We start switching on the temperature, and the superfluid phase gets smaller and smaller until it eventually completely disappears. All right, and this means that at some point we just hit classical correlations, and the superfluid is no longer there. Same thing, we can see it on the occupation number. As we switch on the temperature, we go from essentially having two phases, not insulator or superfluid. As we switch on the temperature, there are these intermediate phases that correspond to a normal gas phase. All right, where we just have a smooth crossover between the different occupation numbers. Now, this was for the pyrochlore lattice in 3D with hardcore bosons. We could also do softcore bosons. But as you know, this is the, I mean, this is justifying our approximations from before using infill theory. The calculations are actually, apart from being extremely efficient, they are also very accurate. Now, we also implemented this in spin models in higher dimensional systems, and there is a very interesting spin model in 3D, which is the Kita F model. Now, the 3D Kita F model is a generalization of the Kita F honeycomb model, okay, but to 3D systems. Now, there are many generalizations of the honeycomb Kita F model to higher dimensional systems. There are papers by Maria Hermans and Simon Trebs about this. They did a full career exactly on this topic. Essentially, you can generalize the Kita F honeycomb model to higher dimensional systems whenever you have a trivalent lattice. All right, and there are many trivalent three-dimensional or high-dimensional lattices, and there are some family of lattices that are also vortex-free in the ground state. And for those systems, for those particular lattices, with the same type of exact solution that applied to the Kita F honeycomb model also applies in this case. Okay, so this is an example of the Kita F model in the hyper honeycomb lattice, which is essentially this lattice right here. It's very similar to stacked two-dimensional honeycomb lattices, okay, but somehow coupled with each other in a funny way. We just defined the Kita F model here with three different types of couplings depending on the direction of the bond, XX, YY, or ZZ. Interestingly, turns out that there are materials that correspond to this type of model, okay, like this one here. And the nice thing for us is that the ground state is vortex free. So there is exact solution at 0 temperature, and it follows exactly the same rules than for the standard honeycomb Kita F antiferromagnet. So the ground state is here on the right-hand side. It's a standard, Kita F triangle. There is an abelian phase when one of the couplings is much larger than the other. In the middle, there is a non-abelian topological phase right here, hosting non-abelian anyons. This is fine. These are the properties of the ground state. Now, what we were interested here was in studying the thermal properties, all right? Now, the thermal properties are very interesting because there are papers claiming and actually showing that the specific heat actually has a double peak behavior. This is kind of signaling two interesting regions in the thermal phase diagram. So at high temperature, there is a peak in the specific heat that corresponds to a crossover. It's not a phase transition, it's a crossover. And this corresponds to the ordering of the spins, okay, of the actual Majorana fermions, all right, at the temperature that is around the coupling, okay. Now at low temperature, there is an actual phase transition, okay, and this corresponds to the ordering of the other quasi-particles that show up in the Kita F model when you map the spins to fermions, which are the gauge fields. So at low temperature, there is this ordering of the gauge fields. At high temperature, there is the ordering of the Majoranas. The low temperature corresponds to transition. The high temperature, there are claims that this corresponds to a crossover, all right? Now we have the tool to simulate this and actually to see this high temperature crossover very, very efficiently and with a lot of accuracy, all right? And that's exactly what we did. We simulated this model using our algorithm for finite temperatures and studied both peaks, actually the high temperature and the low temperature one, but we focused for obvious reasons in the high temperature one because that was the one that is better adapted to our algorithm. Okay, is the one that involves, the simulations are more accurate, okay, essentially because the correlation length is smaller. And well, the reason for this is that if you go to a lower temperature phase, you're closer to the ground state, there is a lot of entanglement, and then we should take into account the effect of the environments in the contractions, which we are not taking into account. So this is the high temperature peak that we observe here, happens around T prime 0.256. You see that it's actually pretty well converged in the high temperature region for bond dimensions up to 6, and we even compare it to some analytical calculations. That's for the specific heat. One can also see other anomalies and things going on in other observables of the system. Here you have, for instance, the spin-spin correlator, but we also study entanglement entropies and so on, and we observe all the time the same type of behavior. Now, we did entanglement scaling of the position of the peak as a function of the bond dimension or the inverse of the bond dimension. So you can see it here for the thermal crossover. It's actually very well converged in the bond dimension. It converges very quickly. It means that, this phase and this crossover at high temperatures actually involves very low correlations. Now, we also did the same for the low temperature peak, which we also observed, but we see a strong dependency on the bond dimension, and actually it was not converged with our simulations. But this is not a surprise because the temperature here is very low. And we know that we are very close to the ground state. There is a lot of entanglement going on. And to begin with, we should be incorporating the effect of the environment in the calculations, which we are not doing, okay? And perhaps introducing some other tricks to achieve larger bond dimension and get this position converged, okay? So that's what we observe, but at least for the higher dimensional, for the high temperature crossover, we see that the convergence of the method is very good. Okay. Now, having said this, of course, if you have a look at the paper, you will see that we also studied other thermal states for different types of Kitaev models. In particular, we also studied the Kitaev-Heisenberg model on the hyperoctagon lattice, which is another trivalent 3D lattice. Again, we did the full phase diagram. We studied the different crossovers and so on. I invite you to take a look if you want. By the way, I noticed that this is on arXiv, but this was already published, so I should update. That. Sorry for that. Good. Now let me move on to the last point of my talk, which is about incorporating non-abelian symmetries in PEPs and two-dimensional tensor networks. Now, there are many different ways of incorporating symmetries in tensor networks. As you know, it's a good idea. If you think that the ground state or the state that you want to simulate has some type of symmetry, it's a good idea to incorporate it in the ansatz if you want to do numerical simulations, because then you are directly targeting the correct submanifold of states that has the correct symmetry, and you are not just optimizing, let's say, over the full Hilbert space, but you are just optimizing on the relevant submanifolds. For the case of symmetries in tensor networks, this is what happens because of Schur's lemma. When you have a symmetric tensor, which is essentially what we have here on the left-hand side, it means that the tensor is invariant. Okay, it will also be covariant, but let's take it invariant under the action of the group. So we have some matrices that correspond to representation of the symmetry group, and the tensor is invariant. This automatically implies that the tensor decomposes in two pieces. There is one piece that corresponds to a degeneracy tensor, all right? And this is the one that has all the degrees of freedom of your tensor, okay? All the variational parameters, everything is in this degeneracy tensor. And then there is another piece that depends only on the symmetry and is fully constrained precisely by the symmetry. And this is what the people call a structural tensor, all right? It depends on the intertwiners of the symmetry group. For a two-dimensional tensor, for a tensor with two indices, this is very simple. They are just matrices. For a tensor with three legs, this starts to be very interesting because the structural tensor is a three-leg tensor that only depends on the symmetries. And this is precisely a Clebsch-Gordan coefficient. Okay, so the Clebsch-Gordans, in the case of SU2, they are the intertwiners of SU2. And these are the tensors that only depend on the symmetry. And they are the ones giving you the symmetry in the system. They are fully constrained. Now, this decomposition is very interesting, as you know already very well, because it implies that a large part of the entanglement in the system is only given by the symmetry, and therefore you can just remove that part from your simulation, focus only on the degeneracy part, which is the one that includes your parameters, and then targeting only this, you should be able to reach very large bond dimensions, better energies, and so on. As you know, this has been implemented in tensor networks for a long time. For SU2, it was implemented in matrix plot states very early already, quite many years ago, by many simulations, McCulloch and many more people in SU2 for two-dimensional systems with PEPs and SU2. It took longer. Okay, people started to implement abelian symmetries for obvious reasons, because they were easier to implement. They didn't involve complicated Klebs-Gordons and so on. For SU2, it took more time. Nowadays, there are different types of libraries for dealing with that, so we can do that. And in our case, we actually wrote a library for dealing with SU2 invariant tensor networks in higher dimensional systems. So this was a project. Actually, this was the PhD project of Philippe Schmoll, who was my PhD student in Mainz and then here in San Sebastian also. We did this using the formalism of fusion trees. There are different ways of implementing this, and at the end of the day, we decided to incorporate fusion trees in the formalism because we thought that this increases a lot the precision of the calculation. Okay. This is how we decompose unit cells of two-dimensional tensor networks. For instance, A here on the upper side, you have how a unit cell of PEPs on the square lattice decomposes into a degeneracy part and also a structural part. Now, the structural part, we decompose it always in terms of trivalent tensors, and therefore we are only dealing with fusion trees here, okay, which correspond to Klebs-Gordon, couplings of Klebs-Gordon coefficients. For projected entangled simplex states, it's kind of more natural for the ones that we use in the Kagom lattice, for instance. This is the degeneracy part, and the structural part is directly given by fusion trees. So we implemented a library using this, targeting only the variational parameters on the degeneracy part, and where the symmetry properties were essentially the rules that were imposed by the fusion trees. Okay, so there are not at any point any Klebs-Gordon being stored in the memory of the computer, because this is just giving you the rules for contracting things. Okay, and that's how we implemented a library for dealing with SU2 invariance in PEPs. We did simulations of a number of models. We started with the spin-1 bilinear biquadratic model on the square lattice, which is this one here. There is an interesting parameter value of the difference between the bilinear and the biquadratic terms, 0.21 pi, at which there is a claim that the ground state is SU2 invariant. And there is a very nice paper actually by Philippe Corbos on this topic. Okay. Now we targeted this point with our SU2 invariant simulations, and here you have an example of the results that we obtained and the entanglement scaling of the ground state energy and comparison with the ones by Philippe. The results by Philippe were obtained using U1 symmetry, which is a subgroup of SU2. And now the first thing that we saw is that, yeah, we get very good energies. So our points are the red ones right here, but these ones were obtained using SU2 symmetry, but the ones obtained with U1 are actually lower. Okay. They look very similar, but they are, let's say, epsilon lower systematically. Now, we don't exactly know how to interpret this. So there may be two situations here. It may be that, well, perhaps because we were using the same unit cell, the same optimization, we were very careful about this. We were discussing a lot with Philippe. And at some point, we arrived to the conclusion that either the ground state is not SU2 invariant, okay, and this is the reason why we are getting lower energies with U1, or SU2 symmetry is just too restrictive for variational calculations. And actually, yeah, this is the symmetry that the ground state has, but it's so restrictive that perhaps for a variational calculation, such as the one that we are doing here, this is restricting too much the answers. So we mentioned here that SU2 may be too restrictive. Okay, this was the main conclusion of our paper, or one of the main conclusions of our paper, but there is still a debate going on whether this is the case or whether the true symmetry here is actually not SU2, as was claimed in some papers, but actually it gets broken down to U1. All right, since we had this toolbox. We also simulated, of course, the spin 1/2 Kagome Heisenberg antiferromagnet. We had to do it, okay, for completeness. And yeah, it works very well. We can get lower energies than without the symmetry. And what we observe is that actually the extrapolations to infinite bond dimension are actually very clean. And the results that we obtained were compatible with getting a quantum spin liquid, because as we increase the bond dimension with the symmetry, we see that there is a crystal structure that actually tends to melt. Last but not least, we also studied the spin 2 Kagome Heisenberg antiferromagnet. Okay, we were not able to reach convergence in the bond dimension here, even using the symmetry. Okay, but we observed that the ground state that we were obtaining, it was compatible with a quantum spin liquid. So, but of course, these simulations were not still converged. We could not go further with our toolbox. So this is a conjecture that I just throw. Okay, an open question. For the ground state of the spin 2 Kagome Heisenberg antiferromagnet is also quantum spin liquid. This is our conjecture. It looks like it is, okay, but of course we need the simulations for larger bond dimension. Last but not least, this is a summary of the energy that we obtain using SU2 symmetry. We can lower the energy, okay, systematically with respect to simulations without symmetry, but we have the feeling that sometimes the symmetry is too constrained, is constraining too much the ansatz, and is too restrictive in the case of higher dimensional systems as compared to, let's say, 1D. Okay, so I see that we are in the discussion time. These are the conclusions. This is, well, essentially you can read them, okay? I don't want to take more time. I know that it has been an intensive workshop, so thanks a lot for your attention.
Thank you for a nice talk. So is there any question or comment? I have a please.
Can I ask a question?
Okay.
So, hello. So, can I ask a question about your SU2 calculation? So, you show that in some cases, your SU2 ansatz has a higher energy than the U1. And my question is that is it correct saying that if the wave function is SU2 symmetric, the PEPS representation of such SU2 symmetric wave function is like you used in the PEPS. So the local tensor satisfy the SU2. And is it the unique description of the SU2 symmetric wave function?
That's a good point. No, it's not unique. It's not unique. So actually, what did I do? Let me go back for 1 second. I have to. Okay. So if you let me go back one more slide, it's not unique. So so we use this for this decomposition in terms of fusion trees, for instance. But it's true that perhaps this is not. I mean, it's a decomposition in terms of trivalent tensors, but this decomposition is also not unique. Okay. And also it depends. You know, we had to play a lot with the different reps that we were keeping in each one of the indices and so on. So maybe there was an extra degree of freedom to play with.
I see. Thank you. Thank you very much.
Yeah.
Okay. Is there other question or comments? Yeah, I have a question about the third topic about 3-dimensional thermal state calculation. Did you try to calculate the second peak structure as on the Kitaev model on 3D honeycomb lattice? Can you calculate the entropy of this system from your method?
Which entropy? The thermal entropy?
Yes, thermal entropy.
Yeah. Yeah, I think we could. I think we will estimate it. That's a good point. Yeah. So I don't remember if we actually did it and included. You will have to excuse me. It's already 1 year half ago. We computed correlation entropies, let's say. But it's true, we didn't compute the thermal entropy. But yeah, it's absolutely possible to compute all the thermodynamic quantities. So we computed here the heat capacity, just as an example, but we can compute the entropy, we can compute everything that has to do with thermodynamics, actually. Yeah.
I see. Well, it may be some result, more additional result for your calculation for this model. Okay. Is there any other question and comment?
Tomotoshi.
Hello. Hi.
Hey.
I have a question about the usage of environment. You have shown you have applied tensor network formulation for 3D quantum system using approximate environment. Okay, so it seems that in higher dimension, those simple environment becomes better and better in higher dimension, increasing the dimension of the system. And thinking about the higher dimensional system, it has been known that static or static-like approximation such as DMFT becomes almost exact in very high dimension. So the question I have is that whether it is possible to prove or make some analytic support for your approximation in higher dimension where it works in well in higher dimension. So do you have any
That's a good point. There are lots of, there is this intuition, okay, and there are lots of based on entanglement monogamy and so on, and there are lots of numerical evidences, okay. But I don't know of any theoretical. It would be nice to have a theoretical proof, yeah, but I'm not aware of anything. The closest thing that I know is of course the people in quantum field theory that, but this is a completely separate topic. It didn't have to do with tensor networks when they study their quantum field theories and they see that for sufficiently large dimension, it's actually mean field and so on. But I didn't see a proof of this for tensor networks, and it would be nice to see, how the bond dimension actually depends on the dimensionality. Yeah.
Okay, thank you.
Is there other question and comment? Okay.